In fact, as you may have noticed, several different states can give rise to the same probability distributions over measurement outcomes. So for instance, here are some examples. The states alpha 0 plus beta 1, alpha 0 minus beta 1, or alpha 0 plus I, beta 1. All of these states here give rise to the same probability distributions of outcomes 0 and 1 upon measuring. And this is a simple consequence of Born's rule. In all three cases, the probability of getting outcome 0 upon measuring is the magnitude of alpha squared. The probability of getting outcome 1 is the magnitude of beta squared. And so if all that we do is simply prepare one of these three states and measure it and repeat this process many times, we won't be able to tell the difference between the three cases. And so a natural question you may have is, then why does it matter at all that we allow alpha and beta to be complex numbers, or even negative real numbers? If all that matters is the magnitude of the coefficient square, then why not just have alpha and beta be positive numbers? After all, we can't tell the difference whether we have beta or minus beta. And so let's take a step back. Right, more generally, suppose we have the state psi, which is equal to alpha 0 plus gamma beta 1, where gamma is some complex number which has magnitude 1. Then you can verify that gamma indeed does not affect the measurement outcome probabilities. In fact, the magnitude of gamma beta squared is equal to the magnitude of gamma squared times the magnitude of beta squared. Recall that this is an identity that we proved in the complex numbers module. And the latter is equal to the magnitude of beta squared, just because the magnitude of gamma is equal to 1. So in other words, the value of gamma does not actually matter to the outcome probabilities as long as the magnitude of gamma is equal to 1. So we refer to gamma in technical jargon as a relative phase. Now, as we mentioned earlier, measurements are lossy. They turn quantum information into a classical answer, and we lose a lot of the information about the coefficients alpha and beta. In particular, at the time that we measure, relative phases do not matter anymore. So we lose all of the information about this relative phase gamma at the time we measure. So then, does relative phase matter at all? Well, the point is that if instead of measuring immediately, we let the quantum state evolve first, and then only measure at a later point in time, then relative phases can matter a lot. And the double-slit experiment is an example of how relative phase can have a dramatic effect. So recall that in a double-slit experiment, there was a stark difference between when we measured whether the quantum particle traveled through the left slit or through the right slit, as opposed to when we simply detect where the particle lands on the detector screen. So in particular, the analogy is that when we observe whether the particle goes through the left slit or through the right slit, we're essentially performing a measurement, which gets rid of a lot of the information contained in a quantum state. So at that point, relative phase does not matter anymore, and we do not see an interference pattern. Now, the point is that if we do not measure in the middle and we simply let the quantum particle hit the detector screen, then relative phases are precisely what ends up contributing to creating this interference pattern that we observe on the detector screen. So in summary, relative phases do not matter at the point at which we measure, but if we instead let the quantum state evolve and only measure at a later time, then relative phases become very important. And in fact, they're responsible for interference phenomena, for example. And interference phenomena are actually crucial to quantum computing, and they're actually responsible for many of the computational advantages that quantum computing gives with respect to classical computing, as we will see actually in one of the later modules.